Good afternoon, students. In the previous session of physics class, we discussed about electric current, charges, flow of charge, and we also discussed about units, charges, electric charges, and its unit. It is a scalar quantity, and this dimension of this flow of charges, flow of charge. Flow of charges per time, that means the rate of flow of charge. Rate of flow of charge is electric current. Electric current. All these concepts we discussed in detail. Expression for current also we are given, and today's class I will continue from these concepts of electric current. Students, hope you remember what is the definition of electric current we are given in last session, in last class. Hope you remember. I given that statement: electric current. It is the rate of flow of charge in a particular direction. The rate of flow of charge in a particular direction, that is electric current. Electric current. It is the rate of flow of charge. Rate of flow of charge in a direction, in a particular direction. This is how we defined electric current, and based on this definition we can write I is equal to dq by dt. It is a rate of flow of charge, or we can also write this is the instantaneous value, or we can write I equal to q by t. Q by t. Based on this q by t, we have unit of charge unit. What is the charge unit? Charge unit is coulomb, right? Coulomb. And time, SI unit of time, that is second per second. Per second, because in denominator, correct? This is a unit of electric current, and coulomb per second we define as ampere. That is ampere. Capital A is the symbol, ampere. Ampere. This is the definition of electric current, and I will continue from this concept of electric current to this Ohm's law. The basic fundamental law of electric current, current electricity is Ohm's law. Ohm's law. This is a fundamental law, one of the fundamental law of electric current. Now this defines that or states that the current flowing through the conductor is directly proportional to the potential difference across the ends of the conductor, provided there is a limitation condition, provided physical conditions such as temperature or pressure or strain, etc. All the physical conditions that remains constant, pressure or strain, temperature, all these physical condition constant, then we can write the current flowing through the conductor is directly proportional to the potential difference. I is proportional to V, or we can write with a constant of proportionality, V is equal to R into I, where R is a constant for a given conductor, and this constant is called as a electrical resistance, where R is known as electrical resistance. Electrical resistance of a given conductor, or we can write R is equal to V by I. R equal to V by I. R is the resistance, so we can define a resistance by using V and I. V is the potential difference, where V is the potential difference, potential difference, and I is the current. Now this V is the potential difference, I is the current, V is the volt. Unit of potential difference is volt. Unit of current is ampere. So that its unit is volt per ampere. Volt per ampere. And this volt per ampere, based on the scientist name George Simon Ohm, he given this statement of Ohm's law, fundamental law. So that by his name unit is given as represented as ohm. OHM, or a symbol is this is the ohm. This is the Ohm's law statement. Current is directly proportional to the potential difference, provided physical conditions remains constant. Physical condition means temperature, pressure, or strain, etc. All the physical condition constant, then only I is proportional to V. Otherwise I is not proportional to V. And this constant of proportionality we can use as a R. R is the electrical resistance for a given conductor. And R is equal to V by I. By rearranging this equation, potential difference divided by current, voltage by current, that is the voltage, volt per ampere, or we can write ohm is the SI unit. This is the SI unit. SI unit. SI unit is ohm. Now this electrical resistance. How you define this electrical resistance? Definition. How you define this electrical resistance? Resistance we can define as it is a opposition offered, resist the material or the body or a wire that resist the flow of charges through it, and that opposition is called as a resistance. So that we can define this electrical resistance as resistance so R is the symbol. We can define this as it is the opposition offered by the material or by the conductor to the flow of charges. The opposition offered by the conductor or material to the flow of charges, that is the meaning of resistance, opposition. And mathematically we define as R equal to V by I. This is a mathematical representation and this is the actual meaning of resistance. And based on this mathematical definition, V by I, it is a ratio of potential difference to the electric current, that is the resistance, electrical resistance. And this electrical resistance of a given material, it depends on certain facts, certain parameter. It varies. The value of resistance varies with the length of the conductor, or it varies with the cross sectional area of the conductor, or it varies with the temperature, or it depends on the material property. So that this resistance we can write as the dependence of resistance. R depends on resistance of a conductor, depends on first point, it depends on the length of the conductor. That is R is directly proportional to length of the conductor. This says that as the length of the conductor increases, resistance of a conductor increases. How we can say as the length increases, resistance increases? For example, I will take a conductor. This you assume it is a conductor of a length L. It has a length L, and its cross sectional area I will take as a is the cross sectional area. and potential difference across this is V. V is the potential difference across this conductor. Now what is the resistance? How we can write resistance of this conductor? Resistance of this conductor R is equal to V by I, correct? R equal to V by I. Now I will increase the length of this wire. This is a wire of length L now. I will increase the wire length. That is, I will take this is the first wire of length L. I will join one more wire of length L to this. Now what happened? Length increases, right? Length increases, length becomes twice. Length twice. As length twice, area remains same here. No change in area. I have not changed area. Area remains same. And this potential difference, first conductor is V, second conductor is V. What is the total potential difference now? It is in the series combination, so that V and V, total potential difference becomes 2V. Now what is the resistance here? R dash is the resistance. R dash is equal to, resistance is potential difference divided by current. Now what is the potential difference here? V plus V, that is 2V divided by current, same current flows here. Here is the current I and here also same current I, because it is in a series combination. I will take current I is flowing through the conductor. What is the amount of charge flowing through this first conductor per second? Same amount of charge is flowing through the second conductor also, so that current I is the same. Is it clear? I is the same, so that I will write I here. Current is I. Now what is the V by I here? What is V by I? V by I is equal to resistance. So that I will write this as 2 times V by I, that is R. R dash is equal to 2 times R we got. Correct? R dash is 2 times R. Now what it means? What I did here, only length of the conductor increased. As the length of the conductor increased, resistance doubles here. Length doubles, resistance doubles. That is the meaning of directly proportional. R is, resistance is directly proportional to length. That means as the length increases, resistance also increases. That is the meaning of proportionality, direct proportional. And resistance also depends on another factor, that is the area. Now how we can write in terms of area? Second point I will write here. Second point. This is the first point. Second point I will write. Resistance is inversely proportional to cross-sectional area. What it means? As a cross-sectional area increases, what about resistance? Area in the denominator, right? Area in the denominator. So that as area increases, resistance decreases. Inversely proportional. As area increases, resistance decreases. If you decrease the area, then the resistance will increase. Resistance will increase. How we can represent this, or how we can prove this? I will take a conductor, same concept. I will take a conductor of length L here, cross sectional area A, and current I is flowing through this, and potential difference is V. For this, resistance R equal to V by I. R equal to V by I. Is it clear? Next, I will increase or decrease the area. For example, I will decrease the area. I will cut this wire into 2 halves along its length. The same conductor, I will cut this wire into 2 pieces, so that the area of each part is A by 2. Here this part also area is A by 2. As you decrease area A by 2, Then what about the current flowing through this? In the total region, certain amount of charge is flowing per second, per time, in the total region. So that 50%, if I reduce area by 2, half, 50% of charge is flowing in the upper half, remaining 50% of charge is flowing in the lower half. So that I can write current becomes I by 2 in the upper half and I by 2 in the lower half. Is it clear? Current becomes I by 2 here, I by 2 here. But what about potential difference? Potential difference is V only. Potential difference V only. Length I have not changed length, right? I changed only area here. Now what about this current and potential difference? Resistance we have to find. I'll take a resistance is R dash here. Resistance R dash is equal to potential difference divided by current. I have to write resistance of each part, right? Resistance of this upper half and resistance of this lower half. Both will be same, right? Upper half and lower half. First I will take upper half resistance. Upper half resistance R dash. Potential difference is same. Potential difference is V. Potential difference is V. Then what is the current? Current in the upper half is I by 2. Current is I by 2. Current is I by 2. Now what I can do? I will take 2 to the numerator. If you take 2 to the numerator, what we get? That is 2V divided by I. 2V by I. What is V by I? V by I is a current resistance. V by I is resistance, so that 2 times resistance. R dash is equal to 2 times R. R dash is 2 times R. Now what we got? What is the meaning of this result? Resistance doubled here, correct? What I did? Area reduced to half. As you decrease area by half, resistance increases 2 times. That is the meaning of inversely proportional. Resistance of a conductor is inversely proportional to area. That means if you decrease the area, one example I have given, students, only one example I have given here, that is I have reduced the area by 2. Now in the similar way, if you add this side by side, 2 conductors, then you can increase area, you can double the area. If you double the area, then what happens? So current becomes double. Current doubles, correct? Current doubles. Then you get the same result we get. Result will be same. So that as you cut the area into half, resistance doubles. That means area decreases, resistance increases. Correct? These are the 2 factors on which this electrical resistance depends. Physical factors given here. Another concept is that is a temperature effect. As the temperature changes, then also resistance of the conductor varies. Temperature effect is there. That I will discuss later. Temperature effect. Another property, another dependence of resistance is that is nature of the material. That is, for example, resistance of copper, resistance of aluminium, resistance of other materials, gold, silver, etc. That is the difference. From metal to metal, its electrical resistance varies. That means electrical resistance depends on material, it depends on nature of the material. That is the meaning of third point. Third point, I'll write here, third point is nature. Nature of the material. Electrical resistance depends on the nature of the material. These are the 3 factors I have represented here. If you combine this first and second equation, that is the first equation is R is proportional to L, and second relation we have is R inversely proportional to area. If you combine these two, I will write electrical resistance is proportional to length divided by area. Is it clear? together, first and second equation. And third one point is the nature of the material. Now how to remove this constant of proportionality? Introduce one constant. What is that constant? R is equal to rho into L by A. R equal to rho L by A. What is this term rho here? What is the term rho? Students, what is the term rho? This term rho represents electrical resistivity, where rho is resistivity, electrical resistivity, or it is also called as specific resistance. Electrical resistivity or specific resistance, that is rho. Representation is rho. Now how to define this specific resistance or electrical resistivity? What is the meaning of resistivity? Specific resistance, it represents resistivity. Yes. Now how to define this? I'll rearrange this equation. Rearrangement is rho is equal to you bring this L and A to other side, then R A L goes to denominator. Is it clear? Students? If you have any doubts or any clarifications required, you can ask in between. You put a comment section. You raise your comment in a comment section. You can ask your questions or any doubts or any clarifications required. In between you can ask. I will clarify here only. Now I will take rho is equal to RA by L. Rho is equal to RA by L. R is the resistance, A is the area, and L is the length of the conductor. Now how to represent its unit? How to write SI unit? Resistance is ohm. Resistance unit is ohm, and area unit is meter square. Length unit is meter. If you take a meter to numerator, power minus 1, that is ohm, meter square, power minus 1 here. Meter square, meter minus 1 cancel out, we get ohm meter. This is the SI unit, ohm meter. Ohm meter is the SI unit of electrical resistivity. Correct? SI unit of electrical resistivity, that is the ohm meter. Now using this equation, I will define this resistivity. Specific resistance or resistivity. How to define? I will take this equation as star. You consider equation star. I will take area of conductor is 1 meter square. 1 meter square. That is if area is 1 meter square. If area is 1 meter square and length is equal to 1 meter, then what about rho? Then rho can be written as R into area is 1, length is 1, that is 1 into R is R only, that is rho is equal to R. Now what is the meaning of this? Students, anyone? Any students? If you take a area of cross section of the wire is 1 meter square, length of the wire is 1 meter, then we got rho is equal to R. What is R? R is the electrical resistivity, right? Resistance. R is electrical resistance and rho is the resistivity. Now we can define resistivity. How to define resistivity? Resistivity or specific resistance is numerically equal to electrical resistance of a conductor of unit length and unit area. That is, I'll write here resistivity is numerically equal to the resistance of the conductor of unit length and unit area of cross section. Unit area of cross section. Unit length and unit area of cross section. Hope you understood this definition, meaning of this term and definition. It is a unit. Unit means one, right? I have taken here one. To define resistivity, I have taken area 1, length 1. That is the unit length and unit area of cross section. Rho is equal to resistance S. Student Suresh Babu has given a correct answer there. That is resistivity is numerically equal to the resistance of a conductor of unit length and unit area of cross section. This is the definition of electrical resistivity, and SI unit is ohm meter. Now students, can you tell me whether electrical resistivity is constant for a given conductor or constant for a material, or it changes from material to material? Any students, can you answer me? Resistivity, whether it is a constant for a given material. Suppose for example you take a copper wire of length 1 meter, copper wire of length 2 meter, copper wire of length 3 meter, or any area of cross section. If you vary length, area, or any dimension, is this value of resistivity changes, or it remains constant? Please answer. Given conductor, someone is resistance is equal to resistivity. Yes. Any questions or any comments? There is one question. Why does resistance of a metal wire increase when its length is increased, even though material remains constant? That is one question raised by Varvez. Students, I have proved here why this how the resistance of a conductor increases with length. I have proved here. I will take if possible I will bring back. See, here I have shown. Hello dear students, Parvez. I have shown here, I proved here. See how this as length increases, resistance of a conductor of a same material changes. See, here is the proof. First what I have taken is a single material, single conductor of length L. Its potential difference is V. Current I flows. Its resistance is R. R is V by I. If you double the length, potential difference, in order to flow same current through this, potential difference here doubles, right? Potential difference doubles, so that we got 2 times resistance. We got 2 times resistance. Is it clear? Yes. Now I will go back our resistivity definition. Any other doubts? If you have any other doubts, you can ask here only. Now I have asked one question here. Students, I have asked one question. Resistivity of a given conductor whether it varies with the length or any other dimension? Answer is no. Answer is no. Someone answered there, Jannavi, Suresh. Resistivity depends on the length of the area and conductor, you said. No, but resistivity of a given material remains a constant. If you take a resistivity of a copper, resistivity of copper, it remains a constant. Copper wire of 1 meter, copper wire of 2 meter, or copper wire of any length, any area, resistivity remains same. Resistivity is a constant. Because we define resistivity for unit length and unit area. For unit length and unit area, it has particular value of resistivity. Whatever be the dimension, the value remains constant. Resistivity is independent on dimension of the conductor, but resistivity depends on temperature. As the temperature varies, resistivity varies. But as the dimension changes, resistivity does not change. So I will write here resistivity is independent on a dimension or size, shape or size. It is independent on shape or size of the conductor. It depends on independent on shape or size, depends on temperature. As the temperature changes, then its resistivity also changes. How it changes, I will explain later. Temperature effect. There is one question asked. Why are alloys like nichrome used for making a heating element instead of pure metals like copper? Because of its resistivity variation. Resistivity. If a material having a higher resistivity, then what happens? As current flows, because of the opposition, there will be a heating effect. Why? What is the meaning of resistance? I will take that example here. Suppose you take a conductor. It has a large number of fixed atoms or ions here in its lattice point. Large number of fixed atoms or ions. Now, as a free electron moves from one end to other end of the conductor. Here, this is a positive side, this is a negative side. Electron moves from a negative to positive side. As electron moves, it suffers collision with this fixed lattice. As it suffers collision, then it deviates from its direction. It changes its direction. Electron is not traveling in a straight line path through the conductor. That is not possible here because of a fixed lattice points here. Large number of fixed atoms exist in the conductor, and that when these electrons encounters or suffers collision with that atom, it deviates from its direction. And this collision, because it suffers collision there, that opposition we call as a resistance, electrical resistance. That is the opposition, and that opposition we call as a resistance. And this opposition depends on material to material. That is the resistance meaning, electrical resistance meaning. Now, as the temperature increases, then what happens? I have to explain that temperature effect. Temperature effect on resistance and resistivity. Both resistance as well as resistivity, that depends on the temperature. As the temperature increases, so then what happens? I will take one example. Temperature of the material increases. As the temperature increases, then what happens? You have a conductor which has large number of fixed atoms here. Here this dot represents fixed atoms or ions. If it is copper, fixed copper atoms. Now as temperature increases, each and every atoms here that gains thermal energy, right? Temperature is heat. Heat is one form of energy. By absorbing this heat energy, what happens? These atoms starts to vibrate in its mean position. Atoms will not be at rest. Atom starts vibrating. This vibrational amplitude of this atom go on increases with the temperature. As the temperature rises, each and every atoms starts to vibrate in its mean position. It vibrates up and down, or to and fro. Because of this vibration of atoms or ions in a fixed position, whatever the probability of collision of moving electrons. Now, when electron moves through this material, now what will happen? Initially, these atoms are not vibrating much. It is almost in its equilibrium point here, almost in its equilibrium position here. So that electron collides and suffers some certain amount of resistance as well as resistivity. Now, as temperature increases, here temperature is increased. As the temperature increased, then what happens? Each and every atom starts to vibrate, oscillate in its mean position vigorously. Due to that vigorous oscillation or vibration of these atoms, this moving electron suffers more collisions. Probability of collision of this electron go on increases, right? That is, as temperature increases, probability of collision of electrons with atoms in the conductor increases. As it suffers more collision, then what about resistance? Opposition also increases. Is it clear? That is the reason why as the temperature increases, resistance increases as well as resistivity increases. Resistance increases. This is the answer for your question. Hope you understood. Correct? Students, if you have any other doubts, you can raise there. I will clarify here only. If the temperature of the metal were doubled, then what is the resistivity also doubled? No. Resistivity is not doubled. That is a good question. That is someone asked there. Good question there. That is, as the temperature doubles, resistivity also doubles. No, relation is different. To explain that with the relation, we have resistivity. Resistivity rho is equal to rho naught into 1 plus alpha into delta theta. This is the equation we have. Hope you cannot understand this, students. If I tell this, here rho naught is the temperature of resistivity at 0 degree Celsius. I will write here rho naught just for your information, because someone asked a question there that is not in SLC syllabus. Rho naught is the resistivity at 0 degree Celsius. I will take in as degree Celsius. Students, what is the SI unit of temperature? SI unit of temperature. Hope you know this, students. SI unit of temperature. Anyone? If you answer, I will continue here. SI unit of temperature. It is not a degree Celsius. Degree Celsius is not a SI system here. But in general, most commonly we use Celsius, degree Celsius, right? Now SI unit is Kelvin. Kelvin is the SI unit of temperature. Kelvin is the SI unit of temperature. Yes, someone answered correctly. Now this is a resistivity at 0 degree Celsius I have taken, where alpha is temperature coefficient of resistivity. temperature coefficient of resistivity, that is a constant for a given material. Temperature coefficient of resistivity, that tells you how that material, its resistivity varies with the temperature. Temperature coefficient of resistivity is a small, means that material, its resistivity does not vary much with the temperature. If temperature coefficient of resistivity is high, means as a temperature, small change in temperature, resistivity varies by large value. Resistivity varies by large value. Is it clear? Is it clear? Yes. Hope you understood. Now, based on this temperature coefficient of resistivity, we can say this resistivity is not varying directly proportional to temperature. It is as temperature doubles, resistivity does not doubles. Yes, yes, okay. Now, this is the concept of temperature effect on resistivity. Now, students, I will go for a very important concept of a combination of resistors. Now, you know what is electric current, potential, and charges concept. Now, I will explain about this combination of resistors. Combination of resistors. First, I will take a series combination of resistors. Series combination of resistors. Now, why this combination of resistors required? Kelvin is scientist name or what? Yes, Kelvin is scientist name. Someone asked a question. Kelvin is scientist name. Scientist name is used as a unit there. Kelvin. Yes. Now here combination of resistors. Students, anyone tell me why we need this combination of resistors? What is the use of combination of resistors? Anyone? Series and parallel. Yes, two types of combination is there. Most commonly we use series and parallel combination. In your SLC level, two combination, that is sufficient. But if you come to PUC, we have mixed combination, series as well as parallel. Different complicated circuits are there, that we will discuss later. For a PU level, PU point, SLC point of view, we need just a series and a parallel combination. Now, what is the use of that combination? That is my question. They are used to pass electricity for circuits. Different answers you are giving there. Now, I will answer this. So, why this combination is required? Series as well as parallel combination. First, I will take a series, then a parallel combination. Now, this is a combination of resistors and its equivalent resistance. Equivalent resistance that we are going to find here. Why that equivalent resistance is? Suppose usually we cannot manufacture resistance of each and every value. For example, 1 ohm resistor, if we prepare 2 ohm resistor, 3 ohm resistor, 4 ohm resistor, suppose we want 2.5 ohm resistance, that we cannot get directly from the market. In such case, by using 1 ohm, 2 ohm, 3 ohm or other values of resistors, we have to make a combination. Using that combination, its equivalent value should be 2.5. For that purpose, we need this combination. We have to learn this combination of resistor to get equivalent values. In a different circuits, the requirement of value of resistance is different. Depending on the requirement, that same value, same specification resistance we cannot get in the market. In such case, to get equivalent value, we have to do the combination, proper combination. By using that proper combination, we can get a specified value of resistance. Now first I'll take a series combination. When resistors are said to be in series, if you connect number of resistors end to end, correct? I will take, for simplicity, I take two resistors. This is a representation of resistors. I'll take R1 here, R2. If you connect these to an external battery of potential difference V, current I is flowing through this. So I is a representation of current. This is the direction of current from positive terminal to negative terminal. This is the positive terminal, this is the negative terminal. Is it clear? Direction of current. Now what is the potential difference across this first resistor R1? I'll write V1. Okay. And here I'll write V2 is the potential drop across the second resistor. As the current flows through the resistor, there will be voltage drop across the resistor. This voltage drop I will write as V1 and V2. Is it clear? Yes, sir. If you have any doubts, yes, sir. Electromotive force. Yes, I will teach electromotive force, EMF. If you require, I will teach that also. We have to connect two or more resistors together in order to, yes, correct. Your answers are correct. I will do that electromotive force later. Once I complete combination of resistors, then I will go for electromotive force. Okay. Now I have taken two resistors in series. Now I have R1 and R2. Assume I don't know what is the equivalent value. Now I have to find out its equivalent value. That means I have to replace this number of resistors. If I have 3 resistor, 4 resistor, number of resistors, n number of resistors, I have to replace this n number of resistors into a single value of resistance. How I can get that? I'll write one equivalent value. Its equivalent circuit is one single resistor. I'll write as a RS connected to the same battery of V. This will produce equivalent potential difference V, and the same current I is flowing through this. Now what I have to do? I'll replace this number of resistors with a single resistor, and single resistor is equivalent to this combination. I assume that a single resistor is RS. Okay. Now I have to find out RS value. How to get RS value? Here same current must flow, right, in the both the circuits. First, in the first circuit, I will take figure 1. This is a figure 1 and this is figure 2. Figure 2 is the equivalent circuits. Okay. I will take figure 1. For figure 1, what is the total potential difference? V is equal to applied potential difference is V. Here drop is V1 and V2. Drop is V1 and V2. You know that potential drop across the combination is equivalent to circuit. Potential difference, that is V is equal to V1 plus V2. Correct? V is equal to V1 plus V2. Using Ohm's law, what is the V? V is equal to I into R, right? Ohm's law. Ohm's law states V is equal to I into R. Ohm's law says V is equal to IR. Substitute V is equal to IR here. V is equal to IR. I will take I is the same throughout. I is the I only. Series combination, same current I flows, right, because same amount of charge delivered by that source is of EMF voltage V. Correct? Yes. What is the question? Sorry students for inconvenience, that power off. Just 1 minute, it will reconnect. Yes. Sorry for students for inconvenience. Now here I'll take last slide. Yes. Now I have to get this equivalent this potential difference. V1 plus V2 series combination. V1 plus V2. V1 is V is equal to I into R1. Resistance is R1 plus I into R2. Same current is flowing, right? Same current is flowing. I into R1 plus I into R2. I'll take this as equation 1. Correct? This is for the first circuit. Now same equation, Ohm's law, apply Ohm's law for the second circuit. That is V is equal to I into Rs. Correct? V is equal to I into Rs. For second circuit, I will take as equation 2. Now you compare equation 1 and equation 2. Compare equation 1 and equation 2. What we get? Left hand side is V, that is the same. So that right hand side must be same, right? That is from 1 and 2, I can write I into Rs, that is equal to first equation, that is I into R1 plus I into R2. I into R2. Here left hand side I, here also I, here also I. Cancel this I, so that Rs is equal to R1 plus R2. This is the equivalent resistance. That is when two resistors in a series, we get Rs is equal to R1 plus R2 is the equivalent resistance. Suppose I have three resistors in series, what I can write? Rs is equal to R1 plus R2 plus R3. For n resistors in series, if I take a n number of resistors, n may be any value, n number of resistors in a series, I'll write Rs is equal to R1 plus R2 plus etc. up to Rn, n number of resistors in a series. For n identical resistors, the most useful equation, if n number of resistors, they are identical in a combination of circuits. That is for n identical resistors, for n identical resistors, R1 is equal to R2, right? R2 is equal to R3, R3 is equal to R4. N number of values same, right? That is I can write Rs is equal to R plus R2 is R plus R3 is R plus etc. up to Rn is also R. Then how to write this as n times R. Rs is equal to n times R. Students, you must remember this equation. If n number of resistors, identical resistors in a series combination, then its equivalent value is n times R, n times each resistance. If there are 10 resistors, 10 identical resistors, each value 5 ohm, 5 ohm. Then what is the equivalent value? For example, 10 resistors, 10 resistors, value of resistance R is equal to 5 ohm. Value of resistance R is equal to 5 ohm each, 5 ohm each. Then what is the value of resistance? Equivalent value of resistance RS is equal to direct answer. Equation of using this last equation we can use last equation. RS is equal to N times R. Direct multiplication. What is N? N is number. Yes, 50 ohm is the correct answer. N is the number of resistors. N is the number of resistors. See, here N identical resistors I given. N identical resistors. N is number of resistors. If there are 10 resistors, N is equal to 10. If there are 20 resistors, N is equal to 20. Like that. That is RS is equal to 10 into 5. That is 50 ohm. 50 ohm is the equivalent resistance. Is it clear? Students, hope you understood how to solve this. I will solve more questions, more problems based on this circuit problems. I will explain how to simplify circuit problems easily, and parallel combination also, parallel combination of resistors. Everything I will discuss in the next session. Students, now for all of you, happy Deepavali from the Excel group of institutions and Excel college sites. Happy holidays, Deepavali holidays. Thank you.